All right, thank you everyone for attending. My name is John Davis. Today I'm going to talk about RISC-V, and the opening question is RISC-V HPC? And I'm here to say RISC-V is HPC. I'll try to stay in one spot for the cameras, but fundamentally, if you don't know who I am, I'm coming from Barcelona Supercomputing Center. We set up a laboratory for open computer architecture, really addressing this. And within the RISC-V community, I'm the chair of the SIG Special Interest Group for High Performance Computing. Today, I'm going to go through what we're looking for in terms of an open HPC stack, what that vision is. I'm going to talk about the SIG a bit so you know what that is if you haven't heard about it. Talk about some of the RISC-V research, and this all builds to convincing you that RISC-V is HPC if you don't know that already. So looking back, I just want to step back in time just to give you a context for where we're coming from and why RISC-V will dominate HPC. So fundamentally, back in the early 2010, 2008 time frame, BSC was promoting ARM as a high-performance computing system, and we built a series of HPC prototype systems with ARM cores from your cell phone. And that was really to develop the software stack for HPC in the ARM ecosystem. That formulated into Mont-Blanc. This was a big project that went through 2020. And what we found is we could play in all the software stack layers. You could do a bunch of stuff, but when it came to the actual hardware ISA architecture, we were very limited. And so we couldn't get to a point where we could do co-design for software hardware. If you fast forward to that time period, 3 years ago, Fugaku was the #1 HPC system in the world for 3 consecutive terms. So that was pretty cool to see a vision of what we thought was embedded only translate into something that could be HPC. So you can see the analogy here with where RISC-V started as embedded, translating into where it could go from a high-performance computing perspective. So just to kind of put that all in context, what we see is there's this opportunity for Europe to kind of help define this open HPC stack from the software down to the hardware. We're limited if we use commodity systems today. Obviously, Linux has driven the way on the software side, and there's a bunch of other open source components that I'm showing here from compilers and schedulers and those types of things that we can leverage. And this software ecosystem extends from IoT all the way to cloud and HPC, so that's pretty cool. The benefit of these open standards and open source software is we have well-defined common platforms, specifications, interfaces, and so that actually helps us accelerate our development. And we believe that hardware can benefit in the same way. And so let's do it for CPUs, GPUs, and other ASICs. So within that space, what we're driving is this view that Europe can help lead the way for this open hardware software stack. We'll base it on RISC-V. It'll be a unifying factor and help us focus and build systems specifically for that. And this open standard, in terms of the ISA, gives us this software compatibility layer that drives the entire ecosystem. So that's pretty exciting, where we can actually envision this future, near future, where everything is based on some open standard or open source component. And so that's really kind of where it goes. There is a lot of work to do. So from that perspective, when we look at these things, we developed the Special Interest Group for High Performance Computing in the RISC-V International to tackle these challenges. And we have a vision and mission, very straightforward. How do we create a RISC-V ecosystem for HPC, right? How do we develop that and foster that moving forward? And this is both on the software and the hardware side. So you have to look at the entire ecosystem and enable it from the edge, high-performance computing, to supercomputers, and not only run legacy code, so this is Fortran and those types of things, but also push that to emerging workloads that might include AI, machine learning, deep learning, either alone or coupled with high-performance computing. So as part of the SIG, we're really driving this open era of HPC, talking about everything from the base hardware components, CPUs, accelerators, coprocessors, those types of things, to the ecosystem of developing that, so verification, compliance, all that kind of stuff, really focusing on the software side initially to support this whole ecosystem and really drive technology independence in that context, specifically for Europe. Some of the things that we've looked at so far, just to kind of give you an idea, we proposed extending the virtual memory system in RISC-V to support the same number of address bits as Intel with 57 bits. We added K, which is basically a user mode and kernel mode page table differentiation. There's opportunities to go to 64 bits, to go to 128 bits, as Krista had mentioned at Supercomputing. All of these things are driving forces to enable RISC-V to be competitive or lead in high-performance computing. This includes accelerators, extensions. I'm going to go into one of the more important things, which is the software stack and how we're addressing that, and then hardware to run so that you can actually have test beds to play with these things. There's also work with adapters, devices, so InfiniBand adapters, GPUs, that kind of stuff, running in RISC-V ecosystems. The challenge we have right now is hardware. So how do we get more hardware into the hands of people? And I hope there's talks here that will tell you that. And there's obviously various vendors here to supply that for you. So I'm excited about 2023. So on the software stack side, friends with Tactical Computing put together a Jenkins a job that basically has a GitHub open repository. You can add a pull request for your software, and then you can run it through an automated flow to actually see if it compiles, right? So the first thing that we need to understand about the software ecosystem is, does it even work, right? Can I compile this to RISC-V? We do it both for GCC and LLVM. You can have parallel builds. The really cool part about this is the Jenkins front end can actually map to multiple different backends. So if you had hardware you wanted to add to the system, you could talk to John Liddell, and he can actually have a pointer for that to do this. It does both native and cross-compilation, so super cool in terms of extending the scope of what you can do and resources. Now, that's the mechanical CI/CD flow. How do we do this from a software perspective? So initially, we're looking at the libraries, because those are the lifting points for all of this in terms of kind of the base building blocks, whether it's FFT or BLAST or those types of things. But we want to capture all these things. So tools, applications, benchmarks, all those things are relevant to the HPC ecosystem as we build that capability to run these things. This will be a broader scope of what you can support and making RISC-V HPC capable. Now, when we look at this, if you were going to risc5test.org, you'd see this a dashboard, and it shows you the different builds. This is relatively old, but it gives you a sense of all the different types of things that you can do and the different targets for LLVM, GCC, and so forth. And so this is public. You can go there now, issue a pull request, and you can actually build your software and see how that works, which is pretty cool. So as I mentioned, the test harness is up on GitHub. You can go there to the repo. You can actually pull this and use it yourself. So if you want a CI/CD flow that worked in your environment for RISC-V, it's out there, right? It's available for you to grab, and then you can do it internally if you don't want to have it public. So again, it's either one of those things where you can contribute to, or you can use the infrastructure and build internally for your own purposes if you have some type of proprietary issues or what have you. So very nice to be able to have a standard Jenkins flow that does this and is ready either to use out of the box, or you can replicate in your environment and go from there. That's part of it. The other part is hardware. So how do you actually run on RISC-V? And there's two HPC-specific test beds in Europe today. One is at BSC, Super5. It's a collection of different types of RISC-V hardware, from unmatched boards to all-winner boards. It has a bunch of exciting opportunities, both physical, soft cores, and emulators. And Excalibur from the UK at Edinburgh, you can run on that as well. So there are resources that if you don't have access to it today, these are ones where you can apply to the organizations, and then they'll give you access according to what that is. So to give you a flavor, we're running a bunch of different boards at BSC, a bunch of different off-the-shelf operating systems, Fedora and Ubuntu, in different numbers of cores and different amounts of DRAM. In general, 12 gigabytes is required to build LLVM or the kernel, those type of things. So from an HPC perspective, I prefer the 16 gigabyte systems. If you're building something, give me 16 gigs or more. So that's the ask. On the software side, as part of the European Processor Initiative, we actually created a whole software stack running on top of that, libraries, tools, compilers to support this that runs today on those systems. So it is a full software stack that you can run. And then if you're trying to get into more advanced things where you want to have new features or test new ideas, we have opportunities to work on FPGAs for soft cores or emulation through various implements, VHave with QEMU and those types of things. So again, there's different mechanisms depending on what you want to do, and these are opportunities to test your ideas and play from there. So in that vein, join RISC-V International. I got a QR code. You just got to click on that, and it'll mail the submission for subscription to the group, and you'll be added. And it's that easy, right? I'm trying to make it as easy as possible. We meet on a monthly basis, and we talk about the various things and try to have action towards the environment to make HPC better. So definitely come join us. Everyone is welcome, free, friendly, respectful, all the good things that is RISC-V. Switching gears a bit, I wanted to look at research in Europe because this has been a big catalyst and driver for what we've been doing is actually have research support the RISC-V ecosystem and go from there. And so historically, it's been a fun journey. In 2019, if you ask people what open source hardware or open standard hardware is, very few people knew. And so it wasn't really on the minds set of very many people. In 2020, we started to see open source hardware appear in the conversation, and so that was pretty cool. And then by 2021, there was a desire to say, oh, hey, RISC-V exists. Well, what's the roadmap for Europe? How are we going to do this? There was a very nice initial report that came out in November of 2021. It's been updated since then. And in the Horizon Europe work programs, this is where you have calls for research. Open source hardware appeared about 6 times. So at least there was a mention of that, so we're getting traction. There was also a consortium, a CSA, that was put together to actually develop a roadmap, so we've made some progress. In 2022, it changed, and now we're seeing a call for building RISC-V both on the hardware and the software. Within the Key Digital Technologies Joint Undertaking, KDTJU, RISC-V was mentioned over 25 times. So this notion of building systems from a research perspective or an innovation, industrialization perspective came on board. Even in the EU Chip Act, there was 5 mentions of RISC-V and open source hardware. And in 2023, I expect there to be a lot more, right? We're aligning within Europe to drive this both on the high performance computing side, Euro HPC, as well as the pieces lower, the KDT, which is anything from high-end processors down to IoT. So that's super cool. In the meantime, there's been a bunch of projects that have formed this, right? Formed this initial seed foundation for RISC-V, starting with the European Processor Initiative. There are 3 different RISC-V accelerators part of that project. In the MEEP project, we're using FPGAs to emulate RISC-V accelerators and drive a larger system ecosystem where we have almost 100 FPGAs built to do that system emulation and do system software testing and software development ecosystem components. eProcessor is another project which gets into the hardware side, and I'll go into some details there, building open source out-of-order cores. EU Pilot is a project spurred out of EPI, which drives overall large-scale system pilot systems for accelerators. And Isolate is a new KDD project, which is high-performance, secure RISC-V processors. There will be much more. So these are funded. There's more to come, which is super exciting. So just to highlight on the hardware side, right, I talked about EPI. Up in the upper right corner is the test chip that they produced out of that with a bunch of different accelerators, vector, machine learning, and stencil, variable precision CPU, so think 128 bits, 256 bits. We have the vector and systolic array coprocessors and MEEP, eProcessor, single and dual core chips with dual socket capabilities is coming out of that research project. The lower right, I'm showing the water tank. Well, it's a liquid immersion tank, plus the accelerators going into a UBB style accelerator board for the pilot, EU Pilot, and there's many others that I haven't mentioned. So as you look at this, there is a groundswell of research and work going towards RISC-V on the hardware side. Likewise, that's true on the software side. So in the MEEP project, we're looking at traditional HPC workloads on the right, all the way to high-performance data analytical workloads in the middle and the left. And that is workflows, TensorFlow, Apache Spark, those types of things. And so making sure that all builds and works in the RISC-V ecosystem really drives the HPC parts. Likewise, in EU Pilot, we've now taken 2 different types of accelerators, a machine learning and stencil or a vector, and we have an entire software stack that has to work in the RISC-V ecosystem. So that's everything from GROMACS, which is molecular dynamics code that's very popular worldwide, to doing video anomaly detection on the AI side, and looking at all the components from libraries, frameworks, and so forth that make that work. So that's a pretty exciting piece from that perspective in terms of putting all that together. So again, we're really driving not only the hardware side, but the software piece as well. So hopefully I've kind of shown a roadmap where RISC-V is HPC. And if you weren't convinced by that, let me add a little bit more. All right, so you're at the RISC-V Summit. You can go across the hall. You'll see a bunch of companies. There are a bunch of companies making superscalar out-of-order application cores, right? I have a non-exhaustive list, so if you want to get on the list, ping me. I'll add you. But this is really looking at folks that are building 1, 2, thousands of cores in this context. And sorry if you're not on this, but definitely want you to be a part of that. AI, machine learning, HPC, this is what these companies are going for. So we already have an industrial component driving this. This is a little bit more fun, but every year at Supercomputing and ISC in Europe, they have a student cluster competition. And this year, part of BSc and UPC had a student group cluster, which took RISC-V and competed against all the big boys, right? You have to compile your code. You have to run a complete HPC stack. All of those things come together, and they won the Fan Favorite Award. So they cobbled together 13 boards. So 7 of them came from BSc, 6 came from University of Bologna through E4, which had packaged them together in a nice rack system. That's the lower things on the bottom on the left. And these kids got together, compiled normal benchmarks, HPL, HPCG, ran different types of workloads, chemistry codes, different things. And so that was exciting. You had up to 3,000 watts per cluster. Because they could only get 13 boards, they were at 300 watts. So obviously they wouldn't win. But it was an interesting aspect of putting together and demonstrating that you could run HPC codes on HPC, on RISC-V hardware. So again, another proof point that we're closer than you may think. Now finally, this is new. This came out maybe 3 days ago. There's going to be a call published on December 16th for a RISC-V hardware software project, part of a framework partnership agreement. This is a fancy consortium within Europe, which is addressing RISC-V hardware and software. I'm providing this for you because it's a public link. Otherwise, I couldn't tell you about it. But this is exciting because we're not only doing all this stuff on the hardware and the software side, targeting HPC ecosystems, HPC centers, adjacent industry, but it's serious money. There's going to be 270 million euros associated with this project. And so this is a very exciting place where we're seeing Europe back this notion that RISC-V can be used for high-performance computing. So fundamentally, one of the main things that we work on is trying to advocate for this ecosystem environment and then build those systems, and there'll be more to come. But this is super exciting. So with that, join me at BSc, right? I get this is my platform to say, come work with us. Everything from applications down to physical design, all those things are fun and we can work together on them. We are fabbing chips in a variety of different technologies, both at BSc and with consortium partners. So if you're into compilers, if you're into architecture, that whole stack, come talk to me. The QR code mails me and says, hey, you're interested in a job. So use that to your benefit, hopefully. And with that, I'm going to stop and give a minute for questions.
Sure.
This is our new building.
We do not have any questions come from the online audience, but over here, questions? Questions? Here.
Question there.
Thank you for this great overview. I was interested in the hardware aspects of this, of these processes that you want to make. So I didn't see any technology node or something like that that you decided on so far. Do you have any plans, or do you have any?
So the chips that we've taped out span anything from 65 nanometer down to future chips will be 12 nanometer. And so from that perspective, we're using both a mixture of TSMC and Global Foundries. We go through Europractice, which is our entry into multi-project wafers. So we will do whatever we can. If you're a company and have access to a lower node technology and want to work with us, happy to do that too. But 65 to 12 is what we've been doing so far.
Okay, I believe we don't have more time for questions, so thank you very much.
Thank you.